Hi there, Serdar Yeglov for InfoWorld. In this episode of Smart Go, we're going to examine how to keep track of the way Go programs allocate memory, and how to stay on top of how that can impact performance in Go programs. Memory allocations in Go are a metric of how efficient the Go program is, not just in terms of how much memory is used, but how much time the Go runtime spends managing memory, and how often the garbage collector needs to clean things up. Fewer allocations means both a more memory-efficient program and a faster one. Now, to talk about this, I need to explain the two different ways Go programs handle memory. The stack, or maybe stacks, plural, and the heap. Stack memory in Go consists of a block of memory, usually about 2 kilobytes, that's allocated to each function call or Go routine, and is local to it. Heap memory is allocated outside of any one function call or Go routine. It's for the sake of the whole application. Variables, allocated memory, can live in either one of these two places, the stack or the heap, depending on where they're created and how they behave. And the rule of thumb is, stack memory is faster, but it's limited. Heap memory is slower because it involves the garbage collector, but it's more flexible. Most simple programs aren't demanding enough for us to worry about whether a variable will live on the stack or the heap. But if you're writing a server, or some program that runs operations in a tight loop, those things may need special attention for how they work with memory. If we have thousands of allocations taking place in a loop, that's going to slow things down. Now, when you compile a Go program, the Go compiler does some work to figure out where best to allocate variables. If we can prove a variable never escapes from its function, that it's always local to that function, then that variable gets placed on the stack. If not, it gets placed on the heap. What's more, the Go compiler can tell us explicitly when variables have to be moved to the heap as a way to be conscious of how to optimize their use. So here I have a very simplified example of how this works. This program has two functions that sort of do the same thing. One takes in an integer and returns the same value incremented by 1. The other performs the same operation, but it does it in a different way. It returns a pointer to a newly allocated variable with that value, not the value itself. So if I want to crunch this program with the compiler and find out where any heap allocations might be taking place, I can just compile it with a set of command line flags, like this. The GC flags flag indicates that I want to pass some additional flags specifically to address how garbage collection and memory management work. And when we do that in conjunction with this flag here, the M flag, that gives us explicit details about optimizations. So if I run this, we're going to get the following output. We learn that B, in the second function, is allocated on the heap because it escapes the function that it's in. See, it's a pointer that's passed between functions, so it's not going to be easy to predict what's going to happen to it. This variable AA, on the other hand, in the first function, does not behave like this. It's a copied value, so its path is predictable, and the variable itself does not leave the function at any time. By the way, side note, you'll notice that I have these two comments, go, no inline, in front of each function. Now this really deserves its own video, but what these are hints to the compiler, and they indicate that the functions in question should not be inlined. In other words, they should not have their code copied to wherever they are called as a performance measure to avoid a function call. If we remove these annotations and we recompile the program, you'll notice that we're going to get a different output. Because one of the things the compiler will try to do is make inlining optimizations. This, in turn, can reduce the number of allocations that are performed in a program. But in this case, I'm deliberately forcing inlining off to ensure that the stack and the heap behaviors that I've been describing here will stay consistent through this example. So back to our main example, and this will lead me, in fact, to the other tool that you can use to inspect a program's allocation behavior, the benchmem flag. In a previous video, linked below, I talked about how to create tests for a given program, and tests can also be used as benchmarks. And that's precisely what I have here. I've created a simple test that also operates as a benchmark for my simple application. Now, when I run this test, like so, with these flags, bench and benchmem, I receive a report that tells me how many allocations per invocation of the tested functions took place. The good news is that I only have one allocation per op, which is in line with there being only one variable escaping to the heap in our operation. Watch this. If I go back to my program and I turn off the calls that generate that escaped variable and then rerun my test code, that number will drop back to 0. Now, it's not realistic at all to expect a given function to have 0 allocations. For instance, if you have a format.printf command, that will automatically create allocations within itself. So if you have that somewhere in a function, you're going to have at least one allocation, and you can't do anything about it, save getting rid of the printf. The goal, though, is not to reduce allocations to 0. What matters is keeping the number of allocations down, especially in functions that are called often. Again, that's why inlining becomes useful. Or when you have a tight loop. And again, you may never get this down to 0, and that shouldn't really be your goal. But you should look for hotspots where allocations do happen, and you should try to minimize them. So, to sum up, Go's runtime controls memory allocations, which can be placed in a heap for the whole process, or into a stack for individual functions. You can use tracing tools to determine which variables end up where, the stack or the heap, and also determine how many memory allocations are performed per operation. The fewer allocations you have, especially in tight loops, the more likely your program's not going to suffer from memory-related performance issues. That's it for this video. If you liked it, leave a comment below. Don't forget to subscribe to the Tech Talk channel on YouTube. And for more Smart Go and more Dev with Serdar, be sure to follow me on Facebook, YouTube, and Infoworld.com.